All right, everybody, let's get this going. We have a weird kind of pivot transition in this class now. We've been talking about integration for so long. We started off the semester talking about applications of different integration problems visually, right? We had all those volumes and surface areas that we were finding using integrals. And then we moved from that to just different integration techniques. How do we find antiderivative families for some of the stranger functions or combinations of functions that we've seen? In Calc 1, we had U substitution, and so this semester we've spent our time adding in a whole bunch of other integration tricks. And now it seems like we're going to just leave integration alone and not come back to it. But I promise we are going to circle back eventually. It's just that we're going to start looking at calculus and integrals through kind of a different lens. And in order to do that, we really have to build up some old kind of theory that you've been spending a lot of time with in algebra classes for functions, but we don't have for sequences. So we're essentially going to kind of make a connection eventually between sequences and functions, and series and integrals. And in order for us to be comfortable with this, we have to build up a bunch of just background on what the heck sequences and series actually are. So that's what we're going to spend a little bit of time doing, and then eventually we'll loop things back to integration and stuff like that. So we're going to start off this video by just defining what sequences are. We're going to talk about explicit formulas and recurrence relations. Those are two different ways of defining a sequence. We're going to find limits of sequences using some limits, so maybe have to brush up on limit rules. Then we're going to talk about infinite series and partial sums, and then we'll talk about how we can tell if an infinite series is converging and what it converges to. So let's get this going. We're going to start off with a quick little introduction to sequences. So here's your intro to sequences. A sequence is an enumerated list or collection of numbers. Most times that we're going to talk about them, they're defined by some sort of a formula or pattern. What we mean when we say enumerated is that they are in a list that we can line up with the first term, the second term, the third term, the fourth term, etc., etc., etc. You can essentially line them up in a row where order matters and number them by the order in the list that they go. So, for instance, you can see A sub 1 is the first term, A sub 2 is the second term, and the third term, etc., etc., etc. This subscript we call an index, and that's the thing that's telling us what order in the list it is. We'll normally talk about the nth term. When we talk about the nth term, we're really just talking about some general term. So if you just pick a random index, grab a random term, what is that? So we normally will use these curly braces to represent a sequence. So you'll see them wrapped up in these curly braces a lot. A, in this case, is like the name of our sequence, like F is normally the name of a function. So if we have this sequence A sub n, you might just see it written as curly braces with an A sub n in there, and sometimes we'll be very specific about what the index is doing. Most sequences that we see, the index does start at n equals 1, and it does count up to infinity. And so for a lot of cases, you won't actually see that index written in there. But sometimes we will, just to emphasize what it is, or if there's some kind of weird things, maybe for some reason your sequence is starting at n equals 3, I don't know, and so your first term is really like the third term. Sometimes we'll index our sequence starting at 0, so you'll have an A sub 0, and that's actually the first term. So those kinds of little nuances, it's sometimes nice to have a little bit of notation just representing what that is. Anyways, here's an example. So the first term, if this we're calling a sequence A sub n, maybe we'll say A sub n is equal to this thing. This is a pretty easy pattern for us to describe. It's just counting up by 2s, or maybe someone will look at this and say, oh, it's all even numbers, right? The positive even integers. So this is a pretty easy pattern or sequence of numbers to describe, and we can say A sub 1 is 2, A sub 2 is 4, A sub 3 is 6, A sub 4 is 8. So these are all the indices on these terms. The first term is 2, the second term is 4, the third term, etc., etc., etc. So that's what a sequence is. It's just going to be, at its core, a list of numbers. We can define these things in a couple of different ways. The main thing that we'll be dealing with probably is going to be an explicit formula. This is just a formula for finding the nth term of a sequence given an index n. So it looks like this. Some function f of n where you put in the term number, 1, 2, 3, etc., etc., etc. And if I put in number 10 for n into this formula, it'll give me what the 10th term is. So for instance, in this example that we've got, if I wanted to find the first term, I just plug in 1 for n. And I've got -1 over 2. So my first term is -12. If I want to find the 15th term, I can just plug in -15. Whoops. Not -15. I can plug in 15, and that's going to be -1 raised to the 15th. All over 2 to the 15. I have no idea what 2 to the 15 is, but I do know that -1 to the 15 is just -1. So I've got this term here. If I wanted the fourth term, then I could say this is -1 to the 4 over 2 to the 4, and that's going to be +1 over 16. So we can get all these different values. What's maybe most important or helpful is to just kind of start dealing with these almost like they're functions. Maybe I'll use this little straight line tool. We can deal with them almost like they're functions, and we can kind of plot these things a little bit. So what we could do is build a table of values for n equals 1, 2, 3, and maybe we'll just do the first 4 terms here. If I put in 1, I said I had -12. If you put in 2, you're going to get -1 squared. That's 1 over 4. Now we'll get -1/8 and then +1/16. Maybe I'll do one more just so I have the first 5. -1 over 32. And then if you want, we can graph these. So graphing a sequence is a little bit weird, mostly because it's not actually a function. And so it's not going to have a lot of the same features. So for us, you'll notice there's not really like a y-intercept here, because for our values of n, we never actually use n equals 0. That doesn't really make sense. And also, it's not really going to be a line. What this is going to be, maybe I should put in some tick marks here for 1 and -1. So we've got like -12 here, and then we had +1/4, and then we had -1/8, and then +1/16, and now I'm just kind of guessing, -1 over 32. And this is our sequence. We don't really connect the dots or anything like that because our sequence isn't defined for any values in between 1, 2, 3, 4, 5, etc. It's not like a function where it can take on real numbers in between the integers. So our maps or graphs of these sequences are really kind of boring. They just look like dots. So that'll be something to just keep in mind. We can do the same thing for this one. We'll just plot a bunch of these things. Grab a couple of terms. So we'll look at the first, second, third, fourth, and fifth term by just plugging these in. So we get a half here. If you put in 2, we get 2 over 5. We get 3 over 10, 4 over 17, and 5 over 26. And we can try and plot these ones. So I'll put my 1 up here, and then I've got 1, 2, 3, 4, 5 on my n-axis, and I can go ahead and just plot all these things. There, 2/5. I don't know where these exactly are. I'm just kind of guessing at this point. A little bit bigger than a quarter, right? There, and that's what this looks like. So we can kind of get an idea for what these sequences are actually doing just by finding a bunch of terms and plotting them, seeing what's happening here. We also have this recurrence relation idea. This is a different way of defining a sequence. This is basically a formula that finds the next term. I should have put a set of parentheses around this. That's how we normally talk about it, the n plus first term. basically this is one more than the one that you're at currently. So given the current term, a sub n, we might find the next one. Now, this is a really kind of narrow definition of a recurrence relation. Probably the most famous recurrence relation or recursive sequence that you know of is the Fibonacci sequence. It's 1, 1, I should put my curly brace on here, 2, 3, 5, 8, 13, 21, etc., etc., etc. And this one is not defined by the previous term, it's defined by the previous two terms. So each term is the sum of the previous two. So this one is just 1 plus 1. And this one is really 2 plus 1. And this is really 2 plus 3, etc., etc., etc. So we're just taking the two previous two terms, adding them together, and getting this. So you can extend this idea of a recurrence relation, but for our purposes, we're really just going to look at this narrow focus where we use the previous term to come up with the next one. So we have to have a starting point for something like this, and then we have to have some sort of an expression, a formula, or whatever, where you put in the last term and to get the next one. Now notice, with this explicit formula, we weren't putting in a term itself, we were putting in an index. So an explicit formula is like a function of an index, and the recurrence relation is a function of a term itself. And so with something like this, we can start by saying, maybe I'll draw my same sort of like table of values. We won't plot these. You could, but we won't. And I'll say, all right, here's n. But this part you're going to find out is less important, because what we're really going to care about is what these terms are. Now, we're told that a sub 1 is 2. But then after that, we've got 3 times 2 minus 1, so that's going to be 5. And now we're going to be putting this in here for a sub n to find our next one. So to find a sub 3, that's going to be 3 times a sub 2 minus 1. So that's 3 times 5 minus 1, so that's 14. And then we have 3 times 14 minus 1. So what's that? 42 minus 1. So we're at 41, probably. Something like that. And so the index itself is less important. What's most important is the term that came before it. So it might be easier to just write it straight out in this little list sequence form. So for this one, we start with half, and then we've got half squared plus 1, which is really a quarter plus 1, so that's 5/4. And then our next term is going to be 5/4 squared plus 1, which is really 25/16 plus 1. So that's 25/16 plus 16/16. So what are we looking at? 41/16, something like that. And then your next term is going to be that 41/16 squared, and I'll leave it here, plus 1, etc., etc., etc. So you just keep recursively plugging in the previous term into this new formula here to find your sequence. So a bit of a different way of doing it. Both of them are useful. Both of them are helpful. In some instances, it might be easier to define one sequence explicitly, or maybe it might be easier to define it using recursion. It might not always be possible to define sequences using both methods, especially if you allow for a bit more complicated recursion. So for instance, the Fibonacci sequence, there's not a nice explicit formula that will just tell you the 15th term. You have to know the 14th and the 13th term to do it. You add those two things together. So there's kind of different pros and cons to both of these things. Here's some examples. What I want you to do is to pause the video and to try and come up with an explicit formula and a recurrence relation for both of these sequences. It's probably a little bit tricky. You'll probably know the pattern before you are able to write out what the formula is or what the recurrence relation is or anything like that. It's probably pretty easy to see what these sequences are doing, but writing it out is not always an easy thing. So take a couple minutes to do that. Pause this video. I'll give you some help along the way. I think it's probably easiest to kind of describe these sequences using the recurrence relation. It's probably pretty easy to just say, look, we're adding 3 to each term. We're adding 3 every time over. And so our recurrence relation is going to start like a sub 1 is equal to negative 1, and then a sub n plus 1 is going to be a sub n plus 3. Meaning, if you want to find the second term, a sub 2, you take the first term and add 3. And you're going to do that every single time. You're going to take the previous term and just add 3 to it to find the next term. Sometimes people will write this way. A sub n equals a sub n minus 1 plus 3. Notice it's the exact same relationship. We're looking at the previous index, adding 3 to get to the next one. So whether you use n plus 1s and n's or n's and n minus 1s, it doesn't matter to me. The explicit formula is a little bit harder. So I want you to think a bit more about that one if you haven't got it yet, but let's talk about this recurrence relation. For this one, we'll start with a sub 1 being 9, and then you can hopefully see that you're just dividing by 3, or you could say multiplying by a third, same thing. So we'll say a sub n plus 1 is going to be a sub n over 3. Or if you'd rather, you can say a sub n equals a sub n minus 1 over 3. I'll probably do this version of it all the time. Use a sub n's and a sub n plus 1s. But you can switch up your indices. It doesn't really matter. Notice all we're doing is multiplying by a third or dividing by 3. So how do we come up with the explicit formulas from here? Because I suspect that if you thought about this for a little bit of time, you probably were able to come up with something like these recurrence relations really quickly and maybe had a harder time coming up with the explicit formula for it. So what I want us to do is to try and think about what it means to add 3 over and over and over and over again, and what it means to multiply by a third over and over and over and over again. What is repeated addition and what is repeated multiplication? Because that's really what we're doing, right? If you want that 5 term here, you're taking -1 and you're adding 3 and you're adding 3 again. You're adding 3 a couple of times over. So how do we come up with a way of expressing that? Take a moment, pause the video again, see if you can come up with that. All right, I went ahead and added them in. These are the ones that we're looking at right here. You can see a little bit about what this is doing. When we were adding 3 each time, repeated addition of 3 is really like a multiplication of 3, right? And so you can say we're going to add 3 n number of times. That's really what 3 times n is. Then I just was fiddling around with this kind of extra term to figure out what was going on. You could notice that if the sequence started one time before it, with one term before it, would start at -4, and then you add 3 to get to -1. Essentially, since n equals 1 here, we're trying to figure out if you add 3 once, that's our starting term. So we start at -4, add 3 once, add 3 twice to get here, add 3 3 times to get here, etc., etc., etc. I do a similar thing with this division by 3. This is really multiplying by a third over and over and over again. So this is really like 27 times a third raised to the n, but I just wrote it this way because it's a little cleaner. This multiplication by a third over and over and over again is really just an exponent. Now, again, it's like you could say our sequence was going to start at 27 if we started a term before that. So that's why I've got 27 here, because I do have to divide by 1 copy of 3, and then divide by 3 again, and then divide by 3 again, etc., etc., etc. So it's just all these exponents of 3 in the denominator, or you could think of it as exponents, or sorry, exponents on 3 in the denominator, or exponents on 1/3. Sorry. So sometimes these are tricky for students to come up with, but we'll get a little bit of practice with these, so hopefully it'll be pretty helpful. Try and notice those patterns that when it looks like you're just adding something constantly every time, that's really probably a product in the explicit formula. And when you're multiplying or dividing something constantly over and over again, that's probably an exponential in your explicit formula. So when we're talking about sequences, a lot of times we'll talk about limits of sequences, which is exactly what it sounds like. You take the sequence formula, the explicit formula for it, and you just apply a limit as n goes to infinity. We see, what is this thing going to count towards? If we're looking at the nth term here in that explicit formula, what's the nth term as n goes to infinity? If that limit exists, we say the sequence converges. If not, we say it diverges. That's the same kind of language that we used with those improper integrals. So that's what we've got here. So for this one, maybe I'll go back and I'll look at this explicit formula and I'll say, okay, this is really a limit as n goes to infinity of 3n minus 4. And this limit should be pretty easy for us to evaluate. I can see pretty obviously that that's going to infinity. That means this thing diverges, which should make sense. this sequence is just going to keep counting upwards forever, counting up by threes, essentially, over and over and over again. It's never going to stop. It's going to go off to infinity. The second one, though, we're really looking at a limit as n goes to infinity of 27 over 3 to the n, or however you wrote it. And you might remember, based on some limit stuff, that when you have something like 27 over infinity, that's really going to 0. So this sequence, we can say, not only does it converge, but it converges specifically to 0. We're going to count this sequence down towards 0. So that's kind of cool. There's not a lot of big difficulty stuff going on here. We just have to make sure that we're okay with dealing with limits. As you can imagine, if some of these explicit formulas here get a little bit more complex, then the limits might get a little bit harder. And so we might have to brush up on L'Hopital's rule and things like that to be able to deal with these limits. But that shouldn't be a big deal. We'll try and help ourselves out as we get through that. That's our intro to sequences. Let's take a look at an introduction to infinite series. An infinite series is pretty basic at its core. You're going to have some sequence of numbers, and all you're going to do for the series is just add them together. So instead of just looking at the pattern or the list of numbers, we're just going to put plus signs in between all of the terms. That can be a little confusing for students because we mainly want to ask the question of like, how can an infinite number of things add up to some sort of a real number sum? And there's a really good, fun example that I like. It's this sum right here. 1 plus a half plus a quarter plus an eighth plus a 16th, etc., etc., etc. And you can see what the pattern is. Maybe I'll write it out for you. We'll use this summation notation. We'll say it goes from k equals 1 to infinity of 1 over... Actually, I might say this. Sorry. There we go. 1 over 2 to the k. The reason I did that is I want my first term to be 0. So I switched my index to 0. I could have put 2 over 2 to the k and had it go from k equals 1 up to infinity and it'd be the same thing. But now when I plug those in, I get these actual terms. So again, you can kind of mess around with your index if you want. So anyways, this thing, we can show pretty conclusively that it actually will count towards something very, very specific. I'm going to do it like this. I'm going to draw a box. And what I'm going to do is just focus on these first terms. And you say, okay, let's pretend I already have a box. And now I'm going to look at half of a box. So that is like this portion right here. Cool. Now I want to add in a quarter of a box. Well, that's just half of what's left. And so that's this portion right here. And now I want to add in a half of that. And I'm going to add in a half of that. And a half of that. And a half of that. And I don't know where I'm at. This is half, a quarter, eighth, 16th, a 32nd, a 64th. Now I can add in a 1 over 128. A 1 over 256, and we can keep adding in these tiny, tiny, tiny portions, and hopefully it's easy enough for us to see that these terms here, this half plus a quarter plus an eighth plus a 16th, that's really just adding up one full box. And so what we really have here is that this adds up to 2. So this is one of my favorite things. I think I told you a while ago maybe that we're going to hit one of my favorite math jokes, and so this is it. So here you go. Ready? Buckle up. An infinite number of mathematicians walk into a bar. The first one walks up to the bartender and says, I'd like a beer. The second one walks up and says, I'd like a half a beer. The third one says, I'd like a quarter of a beer. And the fourth one says, I'd like an eighth of a beer. As the fifth one is walking up, the bartender slams down 2 beers and said, you guys need to know your limits. I think that's a pretty funny joke. Anyways, that's my dumb math calculus joke because this series converges to 2. Anyways, the way that we're going to figure out if a series converges or not is by looking at these partial sums. So a partial sum is just a finite sum, not an infinite series, of just the first n terms. So if I wanted to find s sub 3, it would just be the first, second, and third terms. It would be the sum from k equals 1 up to 3. And we'll just count up only some of the terms. So s sub n is just the first n terms. S sub 100 is the first 100 terms. And here's our big result. If the sequence of partial sums, S sub 1, S sub 2, S sub 3, S sub 4, converges to some real number, then we say the infinite series associated with it converges to L. And essentially, the math notation looks like this. We can, instead of looking at a series counting up to infinity, count it up to n and apply a limit. But then, this thing is the definition of S sub n, the partial sum. And so, if that sequence converges to L, then that's what our series converges to. If the sequence of partial sums diverges, then we say the infinite series diverges as well. All right, so what does this actually even look like? Let's try and mess around with this. What we have to do first is just write down some of the partial sums. So I gave the direction to just write down the first 5. S sub 1 is going to just be the first term. So this is 1 over 1 times 2, or half. S sub 2 is going to be 1 over 1 times 2 plus the second term, when k is equal to 2, 1 over 2 times 3. Or what you'll notice is that it's half plus a sixth. It's S sub 1 plus the next term. I should probably write out what that is. What's that? That's going to be 3/6 plus 1/6, so that's 4/6. So that's 2/3. S sub 3 then is 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over 3 times 4. It's the first 3 terms added up. Or you could say it's 2/3 plus the last next term, because we already know what a half plus a sixth is. So that's going to be 1 over 12. All right, so I got to do arithmetic in my head. I should have probably written this down while the video was paused, but whatever. 2/3 is really 8 over 12 plus 1 over 12 is 9 over 12. That's really 3/4. Pretty sure. S sub 4 then is like the first 3 terms plus the 4th term, but I'll just say it's 3/4 plus the 4th term, 1 over 4 times 5, or 1 over 20. Sorry. There we go. And that's going to be 15 over 20 plus 1 over 20. That's 16 over 20, which is 4/5. And maybe we'll start to be able to notice a pattern in the sequence of partial sums. I got to do one more. This is 4/5 plus 1 over 5 times 6. 4/5 plus a 30th is going to be 5/6. I can tell because I can see really easily what this pattern actually is. So what we want to do now is to come up with, I should see, did I give myself extra room? No. We want to come up with the general form of S sub n. Now, I don't want to write out all the nth terms, right? All the 1 over 1 times 2 plus, because this is really what S sub n is, 1 over 2 times 3 plus 1 over 3 times 4 plus forever and ever and ever, or maybe not forever, but up until we get to 1 over n times n plus 1, and then we stop. But if I don't know what n is, then I don't know what all the terms are. But I can see what the pattern is, right? S sub 1 was a half. S sub 2 is 2/3. S sub 3 is 3/4. S sub 4 is 4/5. S sub 5 is 5/6. This is probably n over n plus 1. And then I can figure out what this limit is. We've got this indeterminate form, but we could use L'Hopital's rule on it, and it really just works out to be 1. That's because the derivative of both of those with regard to n are 1, or you could say these are both polynomials, same degree, so we could look at the leading coefficients, whatever. But either way, we got to get up to snuff on our limit stuff. What that means is that this sum from k equals 1 up to infinity of 1 over k times k plus 1 converges to 1. Cool. Now, that's going to end up being a lot of work for us sometimes to actually find that sequence of partial sums, to actually go through all of the work to try and come up with a general form for S sub n. And so in some cases, that's just going to be way harder for us. But we're going to keep investigating infinite sequence or series and infinite series. Oh my gosh, sorry. Sequences and infinite series. There we go. We will probably talk about sequences a tiny bit more, but most of our time is going to be spent on infinite series.